Okay, so we're going to continue with number 3, where it asks us to calculate the pH when we combine a solution of a strong base with a weak acid. So this is neutralization. Once you realize that you're adding a strong strong acid with H ions or strong base with OH ions, there's going to be neutralization. And so when the neutralization occurs with the weak acid, if there's excess weak acid, then there will be a buffer that forms afterwards. If there's excess hydroxide ions, there's not a buffer, and the pH will just depend on the hydroxide concentration. So I'll walk through this one. So that you start with a neutralization reaction. So if it's sodium hydroxide, we're just going to show the OH ions. Try to write a net ionic equation. And the acid is benzoic acid, so it's C6H5COOH. So we know that this is a weak acid, and we'll understand it's a carboxylic acid because of the COOH bonded there. And so the OH and the ionizable H from the acid will make water as it neutralizes. And then we're left over with this ion C6H5COO, which is benzoate with a negative charge. So when you do the neutralization, it's good to analyze the amount of reactants that you have. We want to compare either moles or millimoles, and sometimes they don't have the unit the way you want it, so you kind of have to rearrange it. So we've been doing a lot where we have the molarity and we multiply by the milliliters to get the millimoles, but this one's a little bit different. So this one says you have 0.0050 moles of the OH, and then for the benzoic acid it tells you the molarity and the volume, and it's a liter. So if we go ahead and multiply 0.015 molarity, which is moles per liter, and you have 1 liter, then you have 0.015 moles of that. So if we compare the amount of moles of OH with the amount of moles of the acid, one of them is the limiting reactant. So because they react in a 1-to-1 ratio, the amount of OH is smaller. So this is our limiting reactant, and we're going to have excess of the weak acid. So each of these will go down 0.005 moles. And so they're both in moles. So that's good. So you're going to have no hydroxide ions left over. And this one's going to have 0.01 moles of this weak acid left over. And we didn't start with any of the conjugate base ion because it was a weak acid. It's like, might be there, but it's negligible. So we treat this as 0 initially. If it was a buffer, and they talked about a buffer solution originally, it would already have some of these and some of these there, so we'd have to account for those there initially. So because this is a reaction that goes to completion, it goes forward, and it depends on the amount of limiting reactant. If these goes down 0.005, then this is going to go up 0.005. So then you analyze what you have left over. So if you have excess weak acid molecules and conjugate base ions that you formed, I hope you realize that that is a buffer. So if we have a buffer, we're going to use the buffer equation. So once you realize the amount of stuff that you have left over, you can go and write down the buffer equation, which is the concentration of H ions is equal to the Ka times the acid over the base. Okay, you have to analyze neutralization first before you use the buffer equation. And when they talk about acid over base, it's the weak acid and conjugate base ion. It's not the hydroxide ions in the base, what we're looking at there. So we're going to try to find the hydrogen concentration, and they give us the Ka as 6.3 times 10 to the negative 5th. So then we can just go ahead, and after we've analyzed the neutralization, we can put the ratio of moles of acid over the moles of the conjugate base. So we have 0.01 moles of the acid left over, and we have 0.005 moles of the conjugate base that form. So in the last example, I used millimoles in my ratio, and the one before that, I used molarity in the ratio, and now I'm using moles in the ratio. Any of those are acceptable, and it's best to use whatever is easiest for the problem. So we're going to simplify for the hydrogen concentration. So that gives us 1.3 times 10 to the negative 4. So we know that if we want to get the pH, we have to negative log the hydrogen concentration. So that works out to be 3.90. And as always, you want to check if that makes sense. So if it started off as a weak acid and we added some strong base, it makes sense that the pH is less than 7 and it's still acidic. Okay, that was number 3. We're going to try to look at